Okay, I think we can start. People will still join us. So, hello everyone, and welcome to another talk in our webinar series. Today, I'm glad to announce we are reaching our 300th webinar. In just a second. Sorry. Okay, so we are glad to announce that we are reaching our 300th webinar, and in these 300 talks, a great amount of astrophysical and computational topics have been covered. Also, a great number of people have worked hard to make it possible since its beginning in 2011. Therefore, a special thanks to each and everyone who has become, in a way or another, part of this amazing project. That said, I'd like to remember that this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel slash LIneA MCTI. Today we have Mireia Montes from the University of New South Wales, Sydney, presenting the talk entitled The Intracluster Light, the Missing Piece in the Galaxy Cluster Evolution Puzzle. Mireia, thank you very much for coming, and the floor is yours.
Thank you very much. First of all, I would like to thank the organizers for giving the opportunity of giving this talk, to an audience that I would normally not reach because, time difference and all of this. So my name is Mireia Montes. I'm a postdoctoral research associate at the University of New South Wales, Sydney. Well, actually, I'm currently unemployed. I'm moving to the Space Telescope Science Institute in the US, and I got the visa today, so this is happening. So today I'm going to talk to you about the work that I've been doing recently. Recently and not that recently, and about the intracluster light, is the diffuse light in clusters of galaxies, but in general about the loss of fast brightness universe. So, in 1995, with a refurbished and shiny new Hubble Space Telescope, the director of the Space Telescope Science Institute at the time, Robert Williams, decided to spend a lot of time studying to a relatively empty area in the sky. He decided to spend a lot of time, a lot of what in Hubble jargon is called orbits. So the younger postdocs, the younger people were very excited about like what you could learn about this, but like the more older astronomers were not that excited. They didn't think that it was the right time to do this kind of thing. They were thinking like more, as it cost a lot of money refurbishing the telescope, it would be wiser to do with the time more things. And they didn't even think that they were going to see that much, investing so many hours in just a piece of a sky. They were not going to see that many things. But turns out, it was a very good idea. So it was such a good idea that they decided to do this kind of thing like 3 more times with, that image. It's this image that you can see here, the Hubble deep field. And, they did that 3 more times with this, the Hubble ultra deep field, being one of the deepest images ever taken and containing some of the farthest galaxies that we know that are, over here in the squares. But we don't have to go that far. We don't have to go to redshift 11. We can, when we dedicate a lot of time seeing things that are closer to us, we can start seeing, we start seeing a lot of things. So first, there was simulations that were showing us that for as you observe, at fainter magnitudes, so, if you go deeper, there were a range of things happening around galaxies. And although it took a little bit of time for observers to catch up, we started eventually we start seeing all these faint structures around galaxies that are starting to emerge. Here, for example, we have M31, our closest massive neighbor, but like we've seen that in other galaxies, that like all this structure that is showing up. So observing these fainter structures, the so-called loss of fast brightness universe, can help us to understand a wide, to explore a wide range of topics. For example, we can see, like the buildup of structure of galaxies with the galaxy halos, or even clusters of galaxies with intracluster light. We can also try to understand these problems that we have, like the missing baryon problem, or the missing satellite problem with loss of fast brightness objects. We can also use some of the objects that we have discovered in the loss of fast brightness universe to try to constrain the properties of dark matter, and we can even study the atmospheres of stars. The problem is that this is not easy. There's a reason why we had to wait such a long time to start exploring this loss of fast brightness universe. One of the problems is that we need a lot of time to observe this loss of fast brightness, but it's not the only problem. So, for example, you're observing inside the Milky Way. So there's a high chance that in your observations that you're going to have a star of the Milky Way, which, like you might like this, but it's a real problem for us. And why it's a real problem that is because of what we call the point spread function. So you have your star, which is a point-like source, which gets through the atmosphere, the telescope, the detector. So through all this path, it gets scattered and reflected. And what it should occupy only 1 pixel, it ends up occupying more than that. And and you can guess that as you go fainter and fainter, this problem gets worse and worse. So like this star occupies more and more pixels. So that's a problem because what you want to study is something that it's intrinsically faint, and you are sending all this you're contaminating your object with this light of these stars. For example, here this is a profile of a BCG of a galaxy and the intercluster light, and you can see here that this part is contaminated by a nearby star, or in this case, we're trying to observe this galaxy over here, and you see that like all the stars in the field of view send light into the area that you want to observe. And this effect, it's not only it's also affecting the object itself. So like in this case, the intrinsic shape of your object, or for example your galaxy, is changing. Changes with the BSF, and the light from the inner parts of in this case the galaxy, it ends up on the outer parts, creating this fake excess that is not like it's not a real one. For example, here you see that all this excess of light that you would think is the halo of the galaxy, it's not. It's created by this effect of sending this light from the inner parts to the outer parts, which you can see here. Another interesting aspect of being inside the Milky Way is that the Milky Way has gas and dust, which as you can guess, like the trend that we've been having is that as you go deeper, you see more of these filaments of dust from the Milky Way. The problem here is that because of this structure that is kind of a filament, it can be like in this case here, it can be very similar to this kind of structures that you can see that you are trying to observe in extragalactic objects. Like in your galaxies, you would think that this might be like a tidal stream, but no, it's the dust of our galaxy. And probably like the worst nightmare of any loss of Brightness astronomers is the sky subtraction. This is very important because if you are not careful in estimating your sky, your background in your images, you can end up basically, eliminating the thing that you're trying to observe. Like here, this is an image of the survey that is being carried out with the Subaru telescope, the Suprime-Cam strategic program. And you can see here that's, like this kind of donut that's basically over subtraction of the other parts of the galaxy. But sometimes it's not that clear. For example, here, this is the Hubble ultra deep field. If you look at the image in the middle, you would think that you are not losing anything, right? That you're not over subtracting. But actually, if you would use like some, more dedicated processing techniques, you will see that you are missing all this light over here. So data processing in this case for loss of brightness it's very important, because if not, you will be missing, or you will have like contamination of like other things. The list that I have given is not exhaustive. There are more other things that you have to take into account, but it's just to give you an idea of like how difficult it is, and to point out that for example the author of this work of the reduction of the Hubble ultra deep field, he said that it took 3 years to actually get it right, because it's a lot of testing of trial and error, and to see like actually uncover like what it's missing there. But well, we are here to know about the intracluster light. So let's dive in. And let's start from the beginning. So in 1937, Zwicky proposed the existence of this material that fill the space between the galaxies in the cluster. That comes from what he called at that time dispersed, disrupted nebulae. And later, in 1951, he actually confirmed his own predictions by observing this material, or this light, in coma. So the first observations of this light were motivated by what they call the missing mass problem. The missing mass problem is so when they were measuring the velocities of the galaxies in coma, the stars, these galaxies were too fast for the cluster to be a cluster. If the only mass that there was, it was the mass, the luminous mass, the mass in stars. So there must be like some mass that they were not observing. So they were thinking that this very diffuse light was a good answer to this answer to this question. Problem is that they very soon realized that the amount of light, which is normally like around 20% of the total mass of the total light of the cluster, and the fact that you have these gradients in color was not enough to explain the discrepancy between the masses that you see. This missing mass problem is what we know now as dark matter. But jumping into today, the availability of large telescopes, we have now better cameras, we have CCDs, and we've been learning new data processing techniques that have allowed us to study this diffuse light in lots of systems, from like the nearby systems like Fornax to clusters at Redshift 1. And we are starting to understand what is this intracluster light. But what is this intracluster light? So observations have shown that as you go deeper and deeper, you have your galaxy that is described, your galaxy or your brightest cluster galaxy, or BCG. This galaxy is described by a model that normally it's a Cersei profile, And as you go deeper and deeper, you start seeing this excess of light at, in the outer parts above your model or your Cirri profile. Those observations also shown that this ellipticity increases with radius, and in some cases there are sharp variations of the position angle of these ellipses, which basically altogether it shows that it's a different stellar component. But not only that, spectroscopy has shown that as you go, to the outskirts of the galaxies, to larger radius, the velocity dispersion of these stars increases with radius till it reaches the velocity dispersion of the galaxies in the cluster. So basically, this is telling us that these stars that form this diffuse light are also forming not only a different stellar component, but also a different dynamical component. So basically, we can define the intracluster light as the light formed by stars that are not bound to any particular galaxy, but they float around following the potential of the cluster. So, in images, deep images like that from the virial cluster, you can see that this light, this diffuse light, is associated with, with these stellar streams that you can see over here and over here. So basically, that is indicating that this diffuse light is associated with these streams, and it comes from the interactions between the galaxies in the cluster. And this is very important because that tells us that we can use this light to understand what has happened in the cluster. So basically, all the interactions that have happened inside the cluster will end up being kind of like we will end up in the intercluster light, and by studying the stellar properties of this light, we can understand what happened in the history of the cluster. And in addition, we can understand how this brighter cluster galaxy or BCGs evolve with time. Simulations show that the growth rate of these galaxies since redshift 1 is steeper than what we see in observations, which are these points. But if those simulations include this formation of this light, of this intracluster light, they agree much, much better with the observations. So basically, by studying the, what's the fraction of light that goes into this component, and you can basically constrain this formation, these models of the simulations, and basically understand how the BCG, the brightest cluster galaxy, evolved with time. Also, simulations show us that there are different mechanisms for the formation of this component, of this intercluster light. So you can create this light by disrupting dwarf galaxies. You can also create this light by the stripping of the stars from massive satellites, also from the violent relaxation after major mergers. So basically, you have like two big galaxies that when they merge, some of the stars will, they will be kicked out and will end up, basically floating around. Another one that personally I think that is my favorite is basically you have another cluster that is merging with your cluster, and this cluster has already some intracluster light that will end up in your in your cluster as intracluster light. And we also have a star formation, in situ star formation. So basically formation happening in this region of the intracluster light. So luckily all these mechanisms provide a different signature in the stellar population of these lights, and by studying the populations, the properties of this light, the stellar population properties, we can infer the origin of this light. So actually, recently, because of the improvements of the, the improvements that I've told you before about, the instrumentation and the data processing, we've been able to study the stellar populations of the intracluster light accurately enough that we can begin to understand how this component forms. We have seen that there are gradients in colors here and in metallicities with radius, which basically, like the metallicity of the stars in this component, in this intercluster light component, basically is telling us that the dominant process of the formation of this light is basically the tidal stripping of massive satellites. However, there are some clusters that present like, some flat gradients, which means that probably the intercluster light in this case it's from major mergers, and of course this is a simplification because this is coming from integrated light. So basically, what you are having is an average of the properties of your of the stars, of the population that you have there, and actually like the reality and the true distribution, it's more complicated. Like here we can see for the Virgo cluster, which is it's closer and it's something that you can study with more detail. That there's a combination of different metallicities. And finally, another property of this intercluster light is that it has shown the potential of tracing the dark matter distribution in clusters of galaxies. So as I told you before, the intercluster light follows the stars in the intercluster light follow the potential of the cluster. So so basically, as like most of the mass of the cluster, it's in dark matter. It's basically it's by studying how the mass distributes, we can study how the dark matter distributes. So in this case, we did that with the Hubble frontier fields clusters, which are deep observations of clusters using the Hubble Space Telescope. And the good thing about this particular set of this particular survey is that they provide mass maps of the clusters, so we can compare the distribution of light in the intercluster light with the distribution of mass of the clusters, and we can see that actually like the comparison, the similarity, it's very good, and we can trace the mass distribution of these clusters up to 140 kiloparsecs. But it's not only that. Simulations have shown that this agreement this agreement continues up to 1 megaparsec. So like the potential of using this intercluster light to kind of have a picture of the distribution of light of the cluster, it's a really cool thing to have fun. But why is that? Why is that important? It's because how the dark matter distributes inside the galaxy clusters. It tells us about the properties of this dark matter. For example, here we have simulations of 4 different flavors of this dark matter, so different properties of the dark matter particle, and you can see that the actual way of the actual distribution in the cluster is very different depending on the properties of this dark matter. So basically, having the ability of having like kind of a picture of how this mass distributes can help us to discern the nature of dark matter. But that was a very brief, very short introduction of the properties of the intercluster light. Now I'm going to tell you about the work that I've been doing here in Sydney. So that's basically unveiling the intercluster light. So we have one of the problems that we have is that we don't have enough number of clusters to study the intercluster light in a statistical way. The depths are usually not enough to be able to reach the intercluster light, and the data processing and or the data processing is not adequate to do that, which is especially horrible for nearby clusters. The thing is that there are some promising instrumentation that we can use to study the Intracluster Light. For example, we have the Suprime-Cam, which is a camera that is in the 8-meter Subaru telescope. It's a 1.5 degree diameter camera, which is, it's basically perfect if we want to study things that are nearby and be able to, for example, do an accurate sky subtraction without being contaminated by the Intracluster Light. So what we did is that we took archival data from this telescope, from the Suprime-Cam, from this cluster, from Abell 85, which is a cluster that is reasonably nearby. It's really extended and is really extended in the sky. The problem is that the current pipeline of this camera, it's producing some oversubtraction of the sky. So and there are some other things that that the pipeline is not doing. So basically, what we decided is to basically process the images ourselves. So that is what I'm gonna talk very briefly now, is the data processing that we've done. So basically, we started with the normal correction of bias and darks, and we then went to the flat field correction. The flat field correction for the loss of harsh brightness is very important because what we want to achieve is a very flat sky, because we don't want gradients or anything that we can that basically bias our measurements. So normally what you take for building the flat fields, the flat field frames, you normally take a dome or twilight flights. But in this case, and particularly because it's such a big camera, those flats will have like some gradient across the image. That is something that we don't want, because it will transfer into our science images. So basically, in this case, what we use is science images to build our flat fields. The problem that we found here is that the flat field also depends on the rotation of the camera. So for example, here on the left, we have a flat made with a rotation, with a random rotation of the camera, while the flat in the middle has a rotation of the camera that is very similar to the rotation of our science images. If we did divide these two flats, we can see that there's a gradient happening, which is around 1% of across the camera, which doesn't seem very much, but actually, if we process the images using these flats, using the flat with the random rotation, we see that there's like some some residuals over here. That is not something that we want. We want something like the image on the right, which is with the rotation of the flats that are similar to the rotation of our science images. So after the flat field correction, we assemble the frame. So the camera has several CCDs, and we assemble the different CCDs in a frame, and we then perform the sky subtraction, which we did it in two steps. We mask everything and we subtract. We mask everything. We measure the sky. We subtract a constant, and in case there's some like residual gradients that like all the other processing has not taken care of, we fit a plane and we fit and subtract this plane. This is kind of conservative because this plane is bigger than the object that we are studying, so it's kind of a safe thing to do. After that, we perform the final coaddition and the final, like the photometric calibration. And on top of that, what we did is the star subtraction and the masking. For the star subtraction, we first need to model the PSF, which is what we did in this kind of weird Frankenstein way. The thing is that the stars that are bright enough so we can characterize the outer parts, the wings of the PSF, are saturated in the center. So we need to use stars of different brightness to characterize, like the different parts of the PSF. So this is the radial profiles of the models that we have for the G and the I band, because we have these two images. This is an example of like the original image, the image with the all these stars subtracted, and the final thing that we have to do is masking everything that is not basically the BCG and the intercluster light, which is basically in images that are as deep as this image is basically everything else. So this is the final image. This is for the G band of Abell 85. This is the G band in black and white, and here we have two zoom ins. This is the BCG of the cluster, and this is one of another galaxy in the cluster. So basically, we're on average for the G and I, we are reaching like around 30 magnitudes per square arc second in boxes of 10 per 10 square arc seconds. So to give you an idea of the improvement, this is the previous deepest image that we have for this cluster, and you can see like that improvement is much better. So all these galaxies over here that you didn't know if they were interacting or not, here you can see that yes, they are, and also you can see all the the tidal tails of this beautiful jellyfish galaxy over here, and it's just with basically 30 minutes of an 8-meter telescope. It's just a short amount of time, and what you can achieve, it's amazing. But this is what we're interested in. This is the BCG and the intercluster light. This with all that we've been doing, we are now in position to study like the intercluster light of this cluster. So what we did is derive the surface brightness profiles for the G and the I bands, and basically you can see here that around from 70 kiloparsecs outwards, you can see this excess of light over the Cirri field that we did to the galaxy, and you can also see that the ellipticity is increasing with radius. In this case, we don't see any change on the position angle of the ellipses. But because we have G and I, we can study the color profiles, the properties, the stellar properties of this galaxy, of this cluster. So we build the color profile, and we see that there are three different regions, the different zones. From up to a radius of 10 kiloparsecs, we see that the color profile is flat, which, as you can see here, that corresponds to the flat part from the surface brightness profiles, which is something that is known. This galaxy has a very big core that is around 10 kiloparsecs, and basically that is telling us that the central part, the stellar populations are very well mixed, so that's why it's flat. From 10 to 70 kiloparsecs, we can see like the typical gradient in color of elliptical galaxies. And from 70 kiloparsecs outwards to around 200 kiloparsecs, we can see again that the gradient is kind of flat again, which is basically telling us that the stellar populations again are well mixed. And combining this that the stellar populations are well mixed with the fact that that it's a different stellar component, it tells us that this is coming from the accretion of the accretion of galaxies. So because we have the color, we can infer basically, like the galaxies that are progenitors of stars with this color, which are galaxies of around 10 to the 10 solar masses, which is in agreement with with our previous works in other clusters. So, sorry, it was a little bit in a hurry, but these are my conclusions. So, like the intercluster light is ubiquitous in clusters of galaxies. So, if you don't have intercluster light in your cluster of galaxies, that means that basically you are not going very deep, and it's so we define this intercluster light as formed by stars that are following the potential of the cluster. So we've seen that the intercluster light encodes the history of assembly of the cluster. So basically, by studying the properties of this light, we can study, like what happened in the past in the cluster. And basically, the addition of this creation of this intercluster light makes simulations agree with the observed mass evolution of the brightest cluster galaxies. Also seen that it's a luminous tracer of the underlying dark matter distribution in clusters of galaxies, and it seems that most of the cluster is formed via the tidal stripping of massive satellites, of satellites that are around the mass of the Milky Way. So that's all I have to say. Thank you very much.
Thank you very much, Mireia, for the very interesting talk. Now we have time for questions from the audience. So questions?
Hi, may I ask a question? This is Basilio Santiago.
Hi.
Okay.
Please go on.
So you didn't, for Abell 85, you didn't show the final image over which the Cirri profile was made to the BCG and the ICL was found, did you? Or perhaps I missed that. After all the star subtraction, all the masking,
Yeah.
how does it look like? I mean,
so
it's quite obvious to see the ICL, right?
Yeah. So yeah, that's this example. So that is just a region of the it's a region of the like the whole image, but basically the image that is basically this is the image, the final image that after subtracting the stars and masking, this is the image that I'm using to like basically do the to derive all the the surface brightness profile and the color profiles.
But I can see the stars there, the PSF.
Yeah. No, I mean just because it looks nice, but basically this is the real thing over here.
Right. So you actually do not interpolate on the masked pixels. You don't do anything in terms of making it smooth.
No.
Ready to fit a two-dimensional profile. You just keep everything.
In this case, I didn't fit to the dimensional profile. It's something that so we've submitted this paper, something that the referee has asked. So yeah, that is something that I'm gonna do. So in this case, what I did is it's a one-dimensional fit, so we can see like when it departs from the Cirri profile.
Right. Okay. So 1D fit. Okay.
Yeah. Just the image is very big. It's the Galactic it's not very happy about it, so it crashes. So that's why we decided to do that. So now I will have to do that with the original image. So it's gonna be interesting to try.
Okay. If I may ask another question, you earlier in the talk, you defined the ICL dynamically as the point where there is an upturn in the dispersion velocity profile.
Yes.
So is that actually observable? I mean, do people actually take spectra of integrated light beyond the profile of BCGs or bright galaxies, or is it just based on dispersion profiles using stars in nearby clusters individually?
So it is really complicated to do that on clusters. So what we've been, like what we can do, it's that is based more on nearby clusters, where you can have like tracers, like globular clusters or planetary nebulae that we can actually get a spectra from. So the first, I'm sorry, this is from the Virgo cluster, and this is with planetary nebulae.
Okay. So no one has actually taken spectra of integrated light from intracluster light and tried to measure dispersion velocities, or like unresolved sources.
They've been doing some spectroscopy of integrated light. Problem is, what they say that it's intercluster light, but they don't reach farther than 50 kiloparsecs, which I think that is still too close to the galaxy.
Right.
Because, for example, in Virgo, 50 kiloparsecs is still still kind of dominated by the central galaxy.
Right. The central galaxy.
So yeah.
Okay. Well, thank you very much, and thanks for staying up late. As I understand, you're in Australia, so that's. Thank you very much.
Okay, thank you, Basilio. More questions? Okay, I suppose there are not more questions.
Everything is ready.
Yeah. Okay, so well, thank you, Mireia. This presentation will be available on our website and LIneA's YouTube channel. For the next week's webinar, we will have Peregrine McGee from the College of the Canyons, and he will talk about the diverse working groups within the LSST, STARS, Milky Way, and local volume science collaboration, including their science goals and relationships across the broader community. So thank you everyone for attending, and a special thanks to Mireia. Everyone have a great day and see you next week. Thank you.